Hello everyone, welcome to the class ECE317 digital signal processing. Today we will keep working on the filters, on the all-pass filter. Okay, it's ECE317 12th week, Wednesday's class. Okay, so last time we discussed the all-pass field, right? All-pass field. All-pass field. All-pass field. Suppose this is the edge of Z is the transfer function. Then we have the feature looks like this. The magnitude of the frequency response will be always equal to 1. And we can also describe it if we write out what is the transfer function. Yeah, you can also write in the Fourier transform in the frequency response, but that needs to write longer, right? So I prefer use Z transform. So if this numerator is some A0 plus A1 Z2 negative 1 plus until some A capital N Z2 negative N, then the denominator you will have just to reverse the coefficient. This is A of n and A of n minus 1 Z2 negative 1 plus until last one A0 times Z2 negative n. The numerator and denominator, they have same coefficients but in different order. And in front of it you can use just a positive or maybe change your sign, also fine. Okay, so this is a all-pass field. For all-pass field, it has a very, it's a very good property about the poles. If P is a pole of H of Z, then what will happen? We will know AN plus AN minus 1. Now P is Z. Z is P. A0 P to the negative n. This will be 0, right? P will be a number you plug in P. Z equal to P. This one, the denominator will be 0. Then the whole fraction will, meaningless because infinite or something. So we call this as a pole, right? As a pole, we have this one. Okay, now I times P to the n on both sides. I just time P on n on it. Then we have A to the n plus A times P to the n. Then A to the n minus 1, P to the n minus 1. I times this one on this one here. And last one will be A0 times P to the n minus n is 0. So just 1 equal to 0. Okay, let me reverse the order. I put the constant, now this constant turn to be A0, right? This is coming from denominator. Constant is AN. Now constant A1, A0. I put A0 in the front. A0 plus next element, it should be this element. It should be A1 times P and plus until A n minus 1 P to the n minus 1 plus A n P to the n equal to 0. So you see, now the order of the coefficient is as same as the numerator part. So what will be the result? You compare the numerator with this one. What kind of conclusion can you have? Is Z inverse equal to P? This will be 0. So Z inverse equal to P will make HZ equal to 0. Or just numerator, right? Numerator is 0. The whole fraction is 0. We make this is 0. So that means P equal to 1, Z equal to 1 over P is 0, of h of z. You see, if you have a p is a pole, then 1 over p will be 0 of h of z. And the reverse, we have another thing. If I do not use p, p is used. I use a q. Okay, if q is a 0 of h of z, then we will have 1 over q is a pole of h of z. Yeah, these two are, it's kind of symmetrically. Yeah, kind of symmetrically. If you have a pole, then 1 over that pole is a 0. If you have a 0, then 1 over that 0 is a pole. Then we can see how about this p and p, 1 over p, and q and 1 over q. Okay, so in graph, we can see like this. If p is here, then what will be q? What will be p inverse? Suppose this is unit circle. Right? This is a j, negative j, negative 1. This is a unit circle. Right? It's a unit circle. If p is here, then which one will be 1 over p? Actually, 1 over p will be this one. This is 1 over p. This is 1 over p. This is p, then this is 1 over p. The feature is the angle, you just change the angle. This is a theta, this is a negative theta. You change the angle. And the length, it is 1 over it. Like here is 2, here will be half. Right? Things like that. So every p, you have a 1 over p will be here. You can say this is a kind of symmetrical, not exactly symmetrical, but the meaning is similar. According to this unit circle, you have a pole outside, then 1 over you have a 1 p outside, then 1 over p will inside the unit circle. And another way, if you have some number inside the unit circle, if you have a number inside the unit circle, if this is a p, then 1 over p will be here. 1 over p will be here. Yeah. Okay. Then the poles and zeros of all positive field will occur as a PS. One is outside the unit circle, one is inside the unit circle, or maybe both just on the unit circle. That is also a case. All right. So this is for all paths. There's a PZ map of all path field. As appears, zeros and poles, they are pairs. The pairs means sum out of or inside the unit circle. Now, outside or inside, out of or inside the unit circle. Right, the pairs, the kind of symmetrical pairs, not exactly symmetrical, yeah, things like that. And or maybe or both on the unit circle. Yeah, things like that. Okay, in my lab to see how it looks like. Yeah. What's wrong? This one. We give all path field. I say it is HA. All right, HA. This will be a field. Okay, what field? I forgot the style of field. Field numerator denominator. Okay, just give numerator denominator will be fine. Right? Just give like this. Okay, so I say I have a system. I say this is all-pass field system. HA means all-pass, H with all-pass. It will be a field of a numerator. Okay, numerator I put like a 1, 2, 3, 4. Okay, this is numerator. The denominator will be reverse of it, so that will be 4, 3, 2, 1. Alright, so we have like this. Okay, numerator and denominator, they have reverse order on the coefficients. Then let's see the PZ map of these HA. Okay, you can see here's a circle, it's dash circle. Let me make it looks more like a circle. This is fine, right? This circle is a unit circle. This circle is a unit circle. And then we have some cross. Each cross is a pole. Each cross is a pole. And we have some circles. Each circle is a 0. Okay, you see? One inside, one outside. You related with unit circle, you can see one inside, one outside. Here's a inside the unit circle, here will be outside the unit circle. This is inside, that is outside. Yeah. They occur as pairs. One inside, one outside. Here all the poles are inside. But sometimes maybe can I have like I don't know, let me try. Let's try 1, 2, 3, 4. 10, 19, and here I put a 19 in front. What do I have? And after these, I gave a PZ map of HA. All right, I run them together. Oh, still all the poles are inside. Can I have a pole outside? I want to find a pole outside. I change a negative. I change like a -3. No. -3. Now here will be also -3, right? Still all the poles are inside. Okay, anyway, this is it's in case you give the different kind of transfer function, then the location of the poles will be different. So here all the example, I'm trying all the poles are inside the unit circle, then all the zeros, they were outside the unit circle, and they occur as pairs, one outside, one inside, one outside, one inside, things like that. Okay, these are the location of poles and zero of all-pass field. Yeah, so one inside the unit circle, one will be outside in the unit circle. But if you have a pole or zero just on the unit circle, then another one will be here. They also as pairs, but both on the unit circle. So this is poles and zeros of the all-pass field. Okay, we can use this feature to change the system from we'll see the stable and unstable. So like you have an unstable system, you can try to add all-pass filter on that system to make the whole system to be a stable one. Actually, we can have more to be minimal phase system. Here we start like this. Okay, here's a PZ map of all-pass field, right? We can also consider PZ map of causal and stable system. For this one what will happen? This one will like this. It is causal. Causal means ROC is Z were larger than some number, right? This is ROC. For causal case, the ROC must be Z larger than some alpha. And for stable, we'll see ROC contain the unit circle. So what will be the RC now? RC, you can see you have a unit circle, and this will be a part of the RC, and RC will be larger than some alpha. So the alpha must be a number inside the unit circle, make the RC looks like this. This is RC. This is RC, right? It must be a area looks like this. It's larger than some number and contain the unit circle. This is unit circle. Here's 1, here's a J, and here's a unit circle. So we always have things look like this. Okay, this is a causal and stable system. The RC looks like this. Then what are the poles? Then the poles, we will see poles, PIs, were certified up to value of all these PI were smaller than 1. Why? Because this circle will go across one of the pole. Remember, like Z minus PI, not Z, the 1 minus PI times Z to negative 1 over this. This one, RC, Z larger than PI. Okay, things like this. So when Z larger than some PI, that PI will be the pole. Now the alpha should be pole, one of the pole. And this pole will be inside the unit circle, right? It's smaller than this unit circle. So we have this, the PI will be smaller than 1. Inside, right? Smaller than 1. So all the poles of a causal and stable system, they will satisfy this condition. They locate inside the unit circle. Inside the unit circle. Yeah, some point like this. Yeah, inside the unit circle. Okay, this is for the causal and stable system. Now we consider the PZ map of the minimal phase system. What is a minimal phase system? Yeah, last time I introduced, right? Minimal phase system, that means both h of z and 1 over h of z, they are causal and stable. Yeah, they're both. You go ahead and go go with a reverse way. Both systems, they are causal and stable. In this case, we call the system H as well as 1 over H. Well, actually, both of them are the minimal phase system. We call this minimal phase system. And what were the PZ map of this kind of H? Okay, now the H of Z, you want it stable and causal, then the poles will look like this, right, inside the unit circle. And for 1 over H, you will have same thing. But these two, they just reverse the numerator and denominator, right? Yeah, 1 over H, use the numerator of H as a denominator. It's a little bit longer. 1 over H, use the numerator of H as a denominator. You got it, right? Okay, so 1 over H, the zeros equal to H, the poles of H, and poles of 1 over H is the same as HZ's zeros. Right. Things like this. Things like this. This happens in generally, right? And for minimal phase system, minimal phase system, both zeros and poles will be inside the unit circle. Alright, so this is the feature for minimal phase system. You check all the zeros and the poles. If all of them they are inside the unit circle, there will be a minimal phase system. Okay, now we can try to use the all-pass filter system on the minimal phase system. You consider a user example to explain it. Example. We have h of z equal to 1 minus 2z to negative 1 times just 1. Okay, I just use this. H is just this one. So this one is causal. We suppose this is a causal system. With h of z is look like this. Then is h of z stable? I would say no. Right? Because you have a pole is 2. 2 is a pole. When z is 2, 1 over z is 1 over 2. Right? Z inverse is 1 over 2. 2 over 2, you get 1. 1 minus 1, you get 0. 1 over 0, that is a pole. So, no. It's not stable. And of course, is h of z minimal phase? Of course, no. Minimal phase means both sides, h and 1 over h, it is a stable one. Now h itself is not stable. Right? It's not stable. So it is not a minimal phase system. Now let HA of z equal to 1 minus 2z inverse over 2 minus 1z inverse. Yeah, this one is not necessary. 1 times it, just z to inverse. Okay, let HA like this. Then I will say HA of z is an all-pass field. Make sense? You change the order of these two coefficients. There will be 1 minus 2 z to negative 1 and the negative 2 plus 1 z to negative 1. And I put the negative in front of it, then I get this one. Right? So this is all-pass field. This is all-pass field. You have a positive and negative in front of it, and the fraction in numerator and denominator, the coefficients just flip the order. Okay, so this is the all-pass field. All-pass field. In other words, magnitude of HA of e to the j omega equal to 1. Oh, here you have to mention this one absolute value is not 1. When you say the all-pass field, you have to use the frequency response. Here should be e to the j omega, not z. Okay, so we have this one. In the all-pass field, we have this one. And furthermore, HA times HZ is what? HA times H is what? HA is 1 minus 2 times z to negative 1 over 2 minus z to negative 1. This is HA. And H is this. It's given 1 over 1 minus 2z to negative 1. So this is a 2 minus z to negative 1 over it. You can write it as here, if you want, just keep this is 1. The 1 minus 1 half z to negative 1, and here is 1 half. You get this one. You get this one. So I can give a name. I say let W of z equal to this. W of z equal to this. Then I will say W of z is a stable system, as well as if we reverse it, no zero. This one only contains the pole without a zero, right? We have pole, no zero. No zero, then you reverse, then the h of z is stable, and 1 over w of z. W of z is stable, and 1 over wz, which is 2 minus z2 negative 1, it is also stable. Right, no pole. Unstable, that means the pole will be larger than the unit circle. Now it's smaller. There is no pole, so of course. Okay, so this one. Now we have what? We have w of z. It is stable actually, and also it's a minimal phase. Minimal phase. It's also a minimal phase system. Minimal phase system. And we have another feature is at the same time magnitude of w of e to the j omega or equal to w is h times this one. It is this one, right? It is this one times this one. But this is all parts. This is all parts. So when you take magnitude, this is 1. So this will be, it is 1 times magnitude of 1 over 1 minus 2e to the negative j omega. Now we have these. We have these. This is what? This is just this is just h, right? It's just h. H is given. Yeah, just h. It is h. We have this. So the meaning is we start from h of z. H of z is not stable, right? I start from this h. H is not stable. It's stable? No, it's not stable. Neither minimal phase, right? Then we define an all-pass field. Let another new field is a combine of the all-pass field and h. I times these two together as w. Then for this w, we will see w is a minimal phase system. As well, w its magnitude is as same as h of z. So the thing like if h is low pass field, then w will also be the low pass field, and actually the magnitude wave is totally same. If h is, for example, it is all pass field, high pass field, then this will be also same high pass field. The magnitude will keep to be same. The angle might be different, but the magnitude to be same, right? So we have this. We can apply these feature when we want to design the system. When we want to design system. All right. Make sense? Yeah. Now we can consider a more complex case. Example 2. We have a system h of z, which is several terms. 1 minus 1 half z2 negative 1 times 1 plus 2 z2 h3 z2 negative 1 and times another 1 minus 1/3, not 1/3, I use 1/3. Okay, I use these. Oh, just 1/3, yeah. 1 minus 1/3 is fine. 1/3, 1/5, 1/4, z2 negative 1, plus, like this. Alright, so we have 3 poles, half, negative 3, and negative 1/4. 2 are small numbers, more than 1, but 1 is large. And the numerator, we also have, so suppose I have 2 terms. It's 1 plus 2, 3, 4. I use 5. Oh, I can use 2. Right? 2 z2 negative 1. And 1 minus is 1/5 z2 negative 1. Okay, we let h of z is this one. So this one is the PZ map. We have 1/2 as a pole, and the -3 as a pole. The -3 is a pole, and the -1/4 another pole. Right, we have three poles. And then the numerator, I have -2 as a 0. Okay, -2 as a 0. And +1/5 as a pole, as a 0. Okay, so the PZ map looks like this. And yeah, here's a -2. The unit circle will be a circle looks like this. Okay, you know what I'm giving. This is a unit circle, should be centered at the original point. Okay, it's not so good, but you know what I'm drawing, right? This is a unit circle. Suppose this is a unit circle. Then we want to find HA of Z and all pass field. So that HR times on this HZ is a minimal phase system. Field. The minimal phase field. Right. So this is the problem. We want to find HR. Then let HR times H is a minimal phase system. So what is a minimal phase system? Minimal phase system, you want all the zeros and the poles, they are inside the unit circle. But now we have two outside. So the thing is, we times all pass field, move these two inside the unit circle. That means you want to cancel this pole and this 0. And add another 0 in the pole, which are inside the unit circle. So the things like that. Alright, now how to do it? To cancel -2, 0, -2, and add pole at 1/-2. We can work like this. We need to cancel this 0, so I need 1 plus 2z to -1 in the denominator. Right? I times this in denominator, then these two can be cancelled. This 0 will be 1 plus 2z to -1. And cancel this, and add the pole at a -2. So here I add, actually this is a 2 plus z to -1. I change the order of these two. So this one satisfies this requirement. I can cancel this -2 with this 0, and also I cancel this pole. No, add a pole. Oh no, this is just cancel the -1 and add a 0. This one cancel this pole and add a 0. And I want add a 0 at -1/2. Okay, so yeah, this is good. And right, this is the poles. Pole is -2 and 0 is -1/2, right? Yeah. Okay. This is for this one. So I just time this. I can cancel this, and I also need to cancel this one. I cancel this one. I use all pass fields. I can cancel this one, and at the same time I add 1 inside. So we also need to cancel that -3. Right? -3. this is a pole, so I want 1 plus 3z to negative 1 and 0. This one will cancel this pole. And for all pass filter, you need to add this one. Right? You reverse the reverse this coefficient. I have the numerator, denominator part. Then the whole thing is all pass. This is all pass. This is all pass. Now I combine these two together. Let H or this is all pass field. It is this one, 1 plus 3 z to negative 1 over 3 plus z to negative 1 times the previous one is this one. It's 2 plus z to negative 1 over 1 plus 2 z to negative 1. Okay. Is this all pass field? Is this an all pass field? I will say yes. You see, this is a multiplication of two all pass field. Then of course the whole thing is all pass field. Right? Whole thing is all pass field. So let HR is like this. Then HR is an all pass double arrow. All pass field. Right. So this is an all pass field. And H or Z times original H of Z, what it is? I just plug in. HR is 1 plus 3 Z to negative 1 times 2 plus Z to negative 1. It's a numerator. And denominator is 3 plus Z to negative 1 times 1 plus 2 Z to negative 1. Alright, this is the HR. And times H. What is H? H is here. Oh, somehow longer. I write it here. Times, okay. Then the numerator I have 1 plus 2 z to negative 1 and 1 minus 1/5 z to negative 1. And the denominator is 1 minus half z to negative 1 and 1 plus 3 z to negative 1. And oh, this is not, this is multiplication. I'm sorry, this is multiplication. Not summation. Yeah, multiplication. And then times 1 plus 1/4 z to negative 1. Okay, so we times these two together. I get the whole thing. Then we do some simplify. We can cancel something. You can see 1 plus 3 z inverse, 1 plus 3 z inverse, they cancel, right? And which one I can cancel? Okay, 1 plus 2 z inverse, 1 plus 2 z inverse, they can be cancelled, right? So any more? Okay, no more. Then the whole thing is a fraction. In numerator I have 3 terms. 1 minus half z to negative 1 times 1 plus 1/4 z to negative 1. Okay, I said I have 3. Yes, 3. This one. 3 plus z to negative 1. This is these 3 terms put together is the denominator. And the numerator I have 2 plus z to negative 1 times 1 minus 1/5 z to negative 1. Alright, we have these. This one is this a minimal phase system. We will check the zeros and the poles. So this one, 0 is 1/5, right? And this one, 0 is negative, let me see, is a negative 1/2, right? When z is negative 1/2, z inverse will be negative 2. 2 plus negative 2 gets 0. So this is a 0, right? And then poles. This one give a pole 1/2. This one give a pole at negative 1/4. And this one give a pole. Oh, I need it. Okay, I divide 3 by both sides. Or I just let this one is negative 3. Negative 1/3. Pole is negative 1/3. Right? Is it alright? Yeah. Okay, now you can see all these zeros and the poles, they are inside the unit circle. The values are smaller than 1. And we can have a map. We can have a map. Zeros at -1/2 and 1/5. Okay, 1/5. Oh, positive 1/5. Not it, right? The 2 zeros. And poles in 1/2. This is 1/5, right? Then in 1/2, here we have a pole. And -1/4. Oh, I'm sorry. What is this? This is 1/5. This is 1/2. This is 1/2. And we have a cross here, right? This is a pole. This is a -1/4. -1/4. So this one according to this one. And this one, this one is I write it as 1 plus 1/3 times the inverse. So 1/3. -1/3. It should be here. -1/3. This is a pole. Right. This is a pole. This is a pole. Is it good? Yeah, I give it again. I need a 1/4. This is negative. I need a 1/4. Why I have a we need a 1/4. Then -1/3. Then -1/2. And this side I need a 1/5, positive 1/5, and positive 1/2. Right? We have these numbers. And this is a cross. This is a circle. This is a cross. This is a circle. And -1/3. Which one is -1/3? This one. This is also a cross. Okay. So we have the graph looks like this. We have 3 poles and 2 zeros. Right. This is the result of the times. After I times these 2 together, I have this. And with the unit circle, and this is -1, this is positive 1, then the unit circle will be this one, right? Surrounded. And all the zeros and the poles, they are inside the unit circle. So we say because all zeros and the poles, they are inside the unit circle. Unit circle. Let's see, HR times H is a minimal phase system. All right, yeah. So you can always work like this. When you have arbitrary field looks like this, then you can try to cancel those poles and zeros outside the unit circle. Here's these ones, right? This is one outside unit circle. This is also outside unit circle. I have 2 outside unit circle. So we want to cancel these 2. Cancel these 2. Use the all-pass field. So that means that all-pass field will contain this one as a denominator, contain this one as a numerator. Then you can cancel these 2. And this is the denominator. You will have related numerator, make this all-pass field. You also need another part related with these to make it an all-pass field. Okay. You can see our HR is this one. We use this one. We use this one, right? Yeah. Here I think about it. Think about it. I use check the poles and zeros. I check this graph to get this one. You can also just look at it here. Right? You check. Okay, here's a 0 larger than 1. There's a pole larger than 1. We want to cancel these two. So we need HR. Oh, no, not this one. Sorry. This is a previous problem. No, what is it? H here. It's here. I have so many papers. They merge together. Okay. This one. Yeah. I want to cancel these two. So want to cancel 1 plus 2 z inverse in the numerator. So I need this one. So this is 1. Is here. You see? So this one contains this in the denominator. So when you times these two, you can cancel this. But just 1 is not enough. You want to make it all pass. So you need 1. I say the inverse way. I put like this. Okay. Right. We change it, flip this coefficient. You get this part. Then this part is all pass. This is all pass. Okay. So this is for cancel this one. We also need to cancel 1 plus 3z inverse in denominator now. So we need to put this in numerator, you see. I say this is a 2, then this is a 2. Right? 2 can cancel this one. Then you also need this part to be all pass filter, so you add a denominator here. This is a 2 with a different order. Right? 2 with different order. You move 3 in the front and 1 in the back. Then you get this one. Then you have your H. You have H, then times H. You have HR, then times HR with H together. Then you have a final answer. This final answer will be a minimal phase system. Alright. Okay, so this is a kind of application of all-pass field. This all-pass field, you can always change your system to be a minimal phase system. That means you can make the system in both sides it is stable and cautious. The system itself is stable, and the inverse of this system is also stable. Of course, both sides are cautious and stable. Yeah. And actually, at the same time, we have another feature. We will keep the magnitude without any change, because all pass field has magnitude 1. Magnitude 1 times on any field you will not change your magnitude. Okay. Alright, that's all for today. See you next time. Bye bye.